And well, despite of what is written in the program, my talk will be a little bit more. So I will talk not about the backend alone, but basically about the overall ARM platform support in LLVM. Well, the motivation is quite simple because if you have everything done in backend, but nothing inside the front end, well, you basically have nothing as a result. So here is the outline of my talk for now. First of all, well, probably some of you are not infrastructure, so I'll give you, well, probably 1 or 2 minute brief introduction about the different subprojects under the LLVM umbrella project. Then I'll present you the status of the different subprojects inside LLVM, namely Clang, compiler RT library, and backend. So here there will be the status as of last release 2.9 we have, and also what will be, well, new things in the next 3.0 release. Next I will talk a little bit about the stuff like how one can track the LLVM sources and contribute back and do whole stuff like that. And last, I also outline several problems which were seen working with the, mostly with the ARM backend stuff in terms of interoperability, the documentation, and everything like this. So, as you might already know, right now, under the name of LLVM, there are a lot of different subprojects. First, surely, and probably this is the biggest part, is just the language-independent optimizer and code generator, which has quite modern library-based design. So, well, it has many stuff inside. Another component and Objective-C++ front-end, which was designed from scratch for speed, compatibility with GCC, and not only, because right now if you track the commit list of Clang, you might see that people work on, for example, compatibility with Microsoft Visual Studio and even some Borland tools. Well, and also another goal for the Clang was not the standalone compiler, but some tool used for indexing, analysis, source-to-source transformation, refactoring, so all stuff like that. Another subproject is the so-called MC subproject, or which stands for machine code. Basically, it's the ground for, let's say, binutils in LLVM world. So it's a library which allows one to build assemblers, disassemblers, also produce object files directly out of backend. Also, recently there was presented debugger in the this debugger basically reuses some part of Clang to do expression parsing and evaluation. It uses some JIT bits. It uses the MC disassemblers to show you what's inside, how the function looks like, and so on. Yeah, and another thing is libc++. It's the reimplementation of the C++ standard runtime library. It has basically 2 goals. First is the full support for the next common C++ standard, and another thing is the performance is also taken into consideration when this library was designed, basically. For this library, it's better to look into the talk which Howard gave during the last LLVM Developers Meeting. I will briefly touch some bits onto libc++, but not too much. So let's proceed to the status. Funny thing is, Clang right now can be named as more or less production ready. Yeah. When I asked Doug DeGregor, several days ago about what does he think about the status of Clang, he said, "Oh, yeah, it seems like it's more or less production ready. How boring! We need to think about new cool features to add into the Clang," stuff like that. So as of now, as of 2.9 release, Clang looks like more or less production quality C, C++, and Objective-C compiler on x86, and also on some ARM cores. It can bootstrap, it can build a lot of crazy sources of C++, including Boost, Mozilla, Qt, and other compiler boosters. And also people report that it can build working FreeBSD system on x86, so including kernel, including user space applications, well, modulo some small glitches inside. And also people report that there is some progress in ARM support for the FreeBSD, and also they do some PowerPC stuff inside and MIPS stuff using Clang in FreeBSD. Basically, the main problem why they do not use Clang on ARM in FreeBSD world is that they still use old ABI, which Clang well, just does not implement. Some amount of ARM-specific extensions are fully supported. For example, the procedural calling convention is fully supported into the backend, and surely the attribute to specify the procedural calling convention for the specific function is also implemented in the front end. Floating point application binary interfaces, all three types are more or less well supported and implemented. All Neon built-ins are fully implemented, and even with some additional extensions. Well, so basically the Neon built-ins inside Clang is, I'd say it's a small superset of what, for example, GCC provides. Well, but otherwise it works quite well. What will be new into the Clang into the next 3.0 release? First of all, the significant progress was made into the support of the next coming C++ release. So well, a lot of features and a lot of different things are already implemented. If you go to the clang.llvm.org website, and there is a special page which includes the C++11 support, and you see that this page has a lot of green things inside, meaning that a lot of features of the next coming standard is already implemented. And surely the corresponding pieces of the C++ standard library are also implemented in the libc++. People add a lot of more useful warnings inside Clang. So they are sometimes they are quite complex semantic checks inside. So well, Clang tends to emit much more useful warnings into the next release. Also, static analysis, I'd say that for maybe past year, maybe year and a half, it was more or less stagnated. But right now, new developers joined static analysis world, and there are a lot of improvements in this area as well. Also, people from Google, they contributed the thread safety annotations. So one can define the semantics of various operations, or semantics of how different threads accessing your variables, and there are semantic analysis checks based on these annotations. So, well, you might have a warning depending on, well, for example, if you are using the variables in non-safe way. More details can be found on the Clang website on the thread safety annotations. Some ARM-specific stuff will be implemented into the 3.0 as well. First of all, I believe it's the last missing piece in the hard floating point ABI, and this was homogeneous aggregate support, and right now it's fully implemented. Next thing is the generic half floating point support inside Clang. So what does here means generic? As you might know, half floating point occurs in two cases. One case is as a storage-only type, for example, for the ARM Neon. Another one as the native time for OpenCL and around. So yeah, the support inside the Clang will be generic. Target will be able to select which flavor of half floating point it would like to use. So there will be native operations for OpenCL and similar stuff, and storage only type for if target supports that specifies that this is the storage only type. So, probably this is one of the feature which we had had inside LLVM GCC, but not currently in Clang, and we definitely should support it. I should outline some things which are connected with the compatibility with standard components of Clang itself. Because people try to just use the Clang as is, as a drop-in replacement for the GCC or their vendor compiler, and then found that Clang commits a lot of warnings or even produce some linker errors and stuff like that. So I should outline some possible compatibility issues if you will try to use Clang for compiling your code base. First of all, Clang is C99 by default. So this means that the inline semantics by default is different in Clang and GCC, because GCC by default is C89. And that means that if you are doing using a lot of inline functions with the old semantics, your code might be broken. Well, you just won't see the bodies of the functions which compiler decided not to inline. Also, in LLVM world, the inline assembler is more strict compared to the GCC ones. So people tend to do various ambiguous stuff with inline assembler. For example, declaring some operand with, say, constraint specifying that variable should go into 64-bit registers, but providing just the 32-bit variable as an argument. And yeah, surely this is the ambiguity, because we do not know how to fill the upper 32 bits of such register. So should we zero extend? Should we sign extend? Should we do not care? Well, and LLVM is much strict in such cases. And if you are using inline assembler in this bogus way, you should fix your code, basically. Another thing is variable length arrays is the C99 feature, and it's not the C++ feature. And it's implemented basically in Clang, but only for the few cases which are more or less direct ones. But basically, I'd say that in the C++, variable length arrays in Clang are not supported, are not implemented, especially if you are using templates as a type for these variable length arrays. Also, Clang is much more standard in C++, so compared to the GCC. And if you go to this web page, you see a lot of cases where GCC accepts the ill-formed by C++ standard code, and Clang does not accept this code at all. What we do not have in Clang at all. So, first thing is we don't support interrupt attribute. That means that if you will want to write an interrupt service routine, either you have to go via another compiler or write some glue code in assembler or something, or find some other solution. Also, ARM in Clang is little endian, so there is no support for big endian byte order for ARM. Well, also, nothing like the universal driver is implemented. Okay, what's universal driver? As you might know, Clang is cross-compiler by design. So since all of the backends, all the targets are just simply registered, you can just link the stuff in and have a new target. And you, in theory, cross-compilation with Clang should be easy. Yeah, just select some other target and you're done. However, this is only theory, and practice is much more hairy, I'd say. Why? Well, compiler is only part of the whole compilation chain, because in order to do cross-compilation, you need to have the standard library in headers, you need to have standard library itself, you need to have linker, and if you want, for example, to have 10 cross-compilers in the one system, surely you need to tell compiler all various paths to libraries, to includes, and you should tell compiler how to invoke the linker and all stuff like that. Yeah. Here is the actual problem. There are multiple ways to solve this problem seen already. Yeah. There are some command line switches, for example, these examples of GCC command line switches. Also, all these M32, M64, mthumb command line switches are also another way of solve of such problem. Multilibs is another way of solve the same problem. There is some other examples, for example, Apple's driver, which just tries to select the whole toolchain depending on the command line you provided to the compiler. Well, but all these are just the approximation solution for the whole problem. So we need to find some generic solution for the cross-compilation in Clang. Well, the basic idea was, well, it's rather simple, because the basic idea is that there should be only single entry point to compiler in the whole system. Yeah, that's kind of easy. So regardless of the target and regardless of the mode you're going to use. So, and then forgot about target triple, forgot about other modes, forgot about CPU settings. Let's stick with just the configuration. Yeah, user provide only configuration. Well, it should be something arbitrary named, and inside this configuration, everything should be defined. So configuration should define all stuff like paths to includes, paths to libraries, well, default command lines for various tools, paths to linker, all this stuff. Surely configuration should be system-wide, for example, for the host compilation. For example, your Linux distribution might provide such configuration because, well, any single Linux distribution has its own way of storing includes and libraries inside the system. So if you look how the stuff is currently done inside Clang, you'll find that there is a long list of hard-coded paths of the includes for various versions of the compilers on various Linux distributions. Another thing that configuration should also be user-wide. Well, and this might be especially good for the cross-compilation. These are only ideas. I think they appeared first maybe 2 years ago, but still no one felt brave enough to drive this project. It's not a lot of code writing for this project, but mostly it's a design problem. One should come with appropriate design for this problem. Well, ask users, ask compiler vendors what and how they want to support inside this universal driver, and then came with just simple design, which should be not so hard to implement. Well, as I said, it's large project, but in design sense, not into the implementation sense. Let's proceed from Clang to compiler RT. Compiler RT is a low-level compiler support library. It contains all various sort of routines like 64-bit arithmetics, soft floating point, all stuff like that. So for Clang, compiler RT is something like similar like libgcc for GCC. Yeah. Right now, inside the compiler RT for ARM, we have all common libgcc functions. For common, I mean 64-bit arithmetics, soft floating point routines, multiplication, division, conversion between integer and floating point, all stuff like that. We even have there some extended ABI functions for ARM. Well, what are some? Here some means those functions for these there are, well, their direct equivalents in the libgcc. We still have to add some more extended ABI functions, well, mostly those which are not directly connected to the libgcc functions. There are some amount of them. Surely such a library, such a compiler support library should contain exception handling runtime. So runtime which do all various dwarf parsing, unwinding, well, all this stuff. We need to have such runtime inside compiler RT. Yeah. Well, probably it's time to change the license of example exception handling unwinding library, which is available at ARM. Well, I don't know. Maybe there is something else I forgot here, but for me it seems that compiler RT to-do list is more or less, well, contains of these 2 points. If I'm mistaken, just let me know. Well, let's proceed to the backend itself. As you might know, LLVM backend is more or less unique because it was not described previously, so it's something like clean room implementation of the backend. LLVM backend operates on 3 different types of area. So here we have something like from highest level down to the lowest level. On the first level, the instruction selection and some scheduling is performed. On the second level, stuff like register allocation and second pass of scheduling is performed. And the third level is basically the same as the target machine code. And the third level is the third IR type is used, well, instead of, you might think is this as something like the just assembler representation inside the memory. Right now, the LLVM backend is quite stable and can generate many different applications, so and generate quite fast code. It supports ARM v5 and next versions of ARM cores. It supports Thumb, it supports Thumb2, it supports VFP, Neon, all these fancy features of modern ARM cores. We also have a special scheduling for Cortex A8 and Cortex A9. Right now, backend emits calls both to the libgcc functions and to the extended ABI functions. So stuff is a little bit messy here. And unfortunately, the JIT on ARM is completely broken as of now. One should ask how fast the generated code is. Well, it's a rather tough question because different compilers usually have different modes used for benchmark compilations. So we saw that different compilers might be, well, and some benchmarks might be biased towards different compilers. However, I present some generic status here. So without going into much numbers, just my generic feeling how well the backend, how fast the code is. I'd say that we still have some problems with middle level optimizers. Why? Well, because if you just grab stuff like nullstone, you see the ratio is something around 80%. And however, good news here is that to test they show rather small ratio, meaning that middle level optimizers are doing, well, quite bad job in 2 particular cases. For other cases, middle level optimizers are performing quite well. So if we will fix these 2 cases, the quality of code and the speed of code will be improved. In average, LLVM generated code is quite good and quite fast compared with GCC and other compilers. So in some cases, we saw a nice 30% speed up. In some cases, we saw slowdown. Some of these slowdowns were identified as the deficiencies of the middle level optimizers and deficiencies of the backends. So, well, these were identified, and I hope that all these issues will be fixed eventually. I should explicitly outline that link time optimization might help performance a lot. So I saw that in some cases, link time optimization might provide nice 50% speed up. What will be new in the next coming 3.0 release? First, a lot of time and work was invested into the Neon code generation. So there will be a lot of improvements in Neon code generation in the next LLVM release. Also, the atomic, the model of atomics inside the LLVM changed recently, and it's much more robust and more complete. So you'll see improvements here as well. We'll clean the mess with calling both libgcc and extended ABI functions. So there will be only calls to the extended ABI functions, not to libgcc ones. So you won't need libgcc, at least for C code. All what you will need is the library which provides you extended ABI routines, for example, compiler-RT or some third-party provided ones. Also, 3.0 release contains completely new register allocator, so there will be a lot of improvements here. Also, 3.0 release contains much better support for inline assembler on ARM, so more constraints are supported. And also, there will be special intrinsics or built-ins for accessing the coprocessor. So previously, we do not have any. One of the important part of the backend is MC library. MC library is a library used to operate stuff on, operate on machine code. So it's on the in-memory representation of the machine code. Current status is the following. As for 2.9 release, the so-called integrated assembler mode was enabled by default on x86. So on ELF, on Darwin platforms, and it performs quite well. However, at the 2.9 release, the emission of ARM binary code was incomplete, and it was incorrect and broken in many cases. Also, the machine code, and library does not support a lot of assembler level directives, especially the ones which are ARM specific. For example, all these directives which are used to emit the unwinding information. So all these fnstart, .safe, .pad, all this. What will be? We expect to have complete ARM assembler and disassembler support in 3.0 release. So this means that integrated assembler mode should be more or less complete there and should work more or less okay. Right now, MCJIT, which is re-implementation of the JIT on top of machine code library, works up to some margin on, at least on ARM Darwin. People reported that it was successfully used for expression evaluation in low-level debugger. Well, but that's only on Darwin, unfortunately. What are still missed inside the machine code library? The first thing, and probably it's the most big project here, is the MCJIT on non-Darwin systems. So one needs to write the ELF loader for the MCJIT and probably filling some other gaps there. Not everything connected with the thread local storage are supported into the machine code, so some relocations are probably missed and maybe something else. Point 3 is connected with the point 1 here, so probably there are some glitches into the ELF emission on ARM, so probably not all relocations are supported, and one should just thoroughly check and fix remaining problems. And another deficiency of the backend right now is that you cannot switch in between different modes inside the one compilation unit. So you might only have, say, the whole compilation unit to be either in ARM mode or into the thumb mode. That's current deficiency. So let me summarize. What is still missed, and what is, really, really welcomed from the community. First thing is the MCJIT, then ELF direct code emission on ARM. Next thing is the exception handling on ARM and runtime library. So one should verify stuff and implement the unwinding library. Also, as you might already know, ARM cores are rather complex. So you might, for example, have the V7 core with Neon, but without VFP. And right now, backend, it does its job using more or less, well, straightforward things like V7 plus VFP plus Neon plus all stuff like that. And if you just switch off VFP, there might be some issues. So different modes and components, so different combination of modes and components might end with some, well, deficiency on the back end. And we greatly appreciate if someone will try to test how well backend supports, well, say, V7 code generation without Neon. Yeah. A lot of testing should be done on the ARM backend alone, and the code should be verified for the performance, for the correction, for the correctness, and all stuff like that. And last point here, and this is a really big project, is the code generation for size. So I should outline that right now support for code generation for size in LLVM is not so good. Oh, one should end with some generic solution and add, for example, optimizations for size inside the middle level optimizers, and teach backend to prefer, well, some instructions over others, and so on. So, now let's proceed to another completely different section. Consider you are some, well, big industrial company, and you are using LLVM inside, and you want to contribute or just use LLVM for some of your projects. How should you proceed? First of all, I should outline that both LLVM and Clang are rather decent amount of C++ code. So as a total, it's more than 1 million lines of code inside. And the community is also rather active. So we have something around 100 active committers, and the LLVM moves and progresses quite rapidly. So code changes also quite rapidly. And as you might know, LLVM has quite liberal license. It's the BSD-like license, so you can integrate and use LLVM in your, well, internal projects and integrate into your products. Probably I can outline two possible usage models with the LLVM sources. First model is just tracking LLVM releases, and another one is always living on top of the tree, so on the main line. Let's consider these two different models. First model is tracking releases. There are surely some advantages because there are large distance in time between necessary code updates, and also releases are usually quite well tested, and there is only a really small probability that there will be some bug there. However, all these advantages are also some sort of disadvantages. Why? Well, meaning that, well, the big time difference between releases, meaning that you have to change a lot when you will want to update your own code base, well, for the next release. Another problem is, consider the case when you found, or you not found, you were hit by some bug into the latest released LLVM version. And you know that this bug was already fixed into the main line. Now you should backport this fix into your private branch, and this might be really non-trivial because, well, the fix might rely on the features which are not yet exist in your private branch. And in most cases, such backports might be quite non-trivial and time-consuming. And, well. Also, I should outline that LLVM releases are time-based, not feature-based. So, meaning that next release surely will bring you a lot of new features, but sometimes some features might be, well, incomplete or even broken into the releases, and they just switched off by default. Well, and no one will freeze or delay a release until some feature will be ready. let's consider another model. So another model is just living on the main line. So there are some advantages, surely. You have fast source updates, and you do not need to backport any bug fixes into your private branch. However, well, all these advantages are disadvantages as well, because you need to frequently update all your code base to track the main line. And also there is a possibility for you to catch the bug which exists only in main line. And it might require some time for you to figure out that this is not your bug, but just the LLVM bug, and to report it and wait until it's fixed or fixed by yourself. All things like this. Surely one can go into the middle and make own releases in between, say, per each month internally, and stick with them. So this is also the possible model. One can ask why one should contribute some changes back to LLVM. Well, the reasons are quite simple. First of all, you can make sure that the changes you contributed back will be inside the main line, and they will be supported and maintained, and well, this way you can just reduce the maintenance cost. Also, if you are interested in some cases, for example, into the code generation for some particular, well, computational kernels, you can just provide some regression tests for such features into the main line, and then you can make sure the main line is, there are no regressions in the main line for the cases which are interesting for you. And also there might be a possibility that the community just, well, extend the code you contributed or fixed if there are some bugs inside. For contribution, there are two different models. First model is the so-called commit after review model. It's quite standard one. You just submit the patch to the mailing list and wait until it's reviewed, and then iterate, fixing all the objections or comments, and wait until no one will have any comments to your page, and basically fix everything until it will be committed. Another model is commit before review model, and this model applies surely for trivial stuff, and also people often read the LLVM commits or CFE commits mailing list, looking for the all patches, going there and review them afterwards, after commits. So well, these are also quite good thing. LLVM has the notion of code owners. So usually these are the people who made a significant contribution to the particular fields, for example, into the backend or, well, LLVM GCC or Clang or C++ support. So this is similar to, well, what are called maintainers in some other projects, but, well, rules are a little bit different here, but still. What are the standard advices here? So how to get your patch accepted? Well, all the advices here are really, really standard. Make sure you make small incremental check-ins, because they're much easier to review and they're much easier to show actual progress. No one likes to review patch bump of 15 or 50 patches into a row. If you are planning to implement some feature, it's a good thing to ask and discuss, especially if the change is huge, into the mailing list beforehand. Also, sometimes different people can contribute onto the same field. So it's good to know who might contribute to the field you're interested in, and ask whether he or she is already working on this particular feature. So there might be a possibility, well, that someone will implement something for you, or to do some task split. Well, this also might be good. And another advice is make sure there are no layering violations across the libraries. It's a good thing. It's a bad thing, for example, for backend to look inside the middle end, or to look from the machine code library into the backend itself. layering should be preserved because it's the basis of the whole LLVM source code organization. Sometimes one wants to add some vendor-specific extensions, well, to Clang or to LLVM or to both. First, how to make these extensions accepted. First thing is to think whether it's possible to make this extension target neutral. For example, when there was a necessity to add naked functions support, it turned out that we can go into the target neutral way, well, and we ended with probably 5 or 10 lines of code just to add naked functions. So right now, the support for naked functions is target neutral, so well, any target can use this stuff. Well, for example, in the GCC, only subset of targets support naked functions, and some supported more or less okay, some are broken, well, all this stuff. Also, it's a good thing surely to come with some good description of your extension. What does it mean? And another thing is you should also provide the exhaustive test suite for your extension. So this way you can make sure that no one will break your code. And also, if possible, one should discuss the changes into the mailing list beforehand. And recently, the rules for extension submission for the Clang at least was more or less specified explicitly. So if you go down to that link, you'll see the precise rules how one should proceed if one wants to add some vendor-specific extensions. Also, I'd like to recommend using JIT and JIT-SVN for working with the mainline sources, because it's much easier to operate on private branches, to do all merges, and do all rebasing inside. We provide public JIT mirror with SVN metadata, so you can just use this as a source of the LLVM code base for you. And let me outline a few problems we had working with ARM backend. First of all, I need to note that the documentation, namely architecture reference manual on ARM, is closed. So you have to be ARM customer just to obtain the documentation about the instruction set. Well, it's rather funny. Also, there is only few information about internals of the course. So all stuff which is important for the compiler writer. So pipeline stages, description of the function unit, reservations, conflicts, all stuff like that. Information about new course is usually closed. However, one can normally just look into the GCC patches mailing list and find that ARM is going to release some other core with some other features. So even if it's not mentioned on the arm.com website. And also we saw rather slow or even no responses to requests or to emails. So I think that's all for me. Thank you.